Hello everyone, thank you for coming and thank you for the invitation. So indeed, I'm Jolien. I'm a third year PhD student at the Institute of Astronomy at the KU Leuven, and I'm working in the team of Professor Leuven, and you can also see my collaborators here on the slides. And today I'm going to introduce you to the topic of how AGB outflows are shaped by the interaction of the wind with one or multiple companion stars or planets. So what is an AGB star? AGB stars are low and intermediate mass stars with an initial mass in between about 0.8 to 8 solar masses, and they have evolved towards the AGB branch, which means they are red giants that lose their outer envelopes through a stellar wind. These stellar winds are quite complex, as you can see in this image here. So in the inner wind, the AGB star is pulsating, and this levitates material up to higher regions, which are a bit colder, and where dust can be formed. And then this dust can get the photons, and then in this way get momentum and can accelerate outwards. And then as the dust can couple to the gas, a wind is launched. So that is why these winds are pulsation-enhanced, dust-driven winds. These winds typically reach velocities of about 5 to 30 km per second, and they have mass loss rates in between about 10 to the minus 8 to 10 to the minus 5 solar masses per year. Because there is a large gradient in the density and temperature within this quite large wind, these AGB stars are very astrochemically rich environments, which makes them very interesting, and also because there is dust present. So about 100 different molecules have already been detected in these winds. And then through their winds, they launch these elements into the interstellar medium, making them very important sources to study if we want to understand this chemical enrichment of the interstellar medium. For decades, it was believed that these outflows were spherically symmetric, so they were also modeled using a one-dimensional approach, which is in high contrast with the successors of these AGB stars being post-AGB stars and planetary nebula, which were known to harbor complex morphologies. But then, as we get better technology and also high-resolution observations, suddenly we got images like this, in which we saw spiral structures appearing in the outflows of these AGB stars. And there were already models existing that show that if you have a companion in such a wind, that you automatically generate this nice spiral structure. So the observations of these spiral structures were clear, indirect detections that there was a companion shaping the wind of these AGB outflows, and showing that these outflows are not spherically symmetric already. So this gave us a good reason to ask for more observations, high-resolution observations of these AGB outflows to study how many of them are asymmetrical. We did this with the interferometer ALMA, and it is the Atomium large program, of which Leuven is the principal investigator. And you can see some results already here. So we have observations of 12 AGB stars with a range in mass and evolutionary phase. And you see that none of these outflows are spherically symmetric. They all harbor quite complex morphologies. So here you see some channel maps of these outflows. And then everything that is red is going away from you. Everything that is blue is coming towards you. So you see that these are quite complex, and they harbor spiral structures, arc-like structures, but sometimes also bipolarity or disks. And by now it is commonly believed that the primary cause of a lot of these complexities is the presence of one or multiple stellar or planetary companions that are hidden within these outflows. This hypothesis is also supported by population synthesis that state that about 50% of these stars is expected to be in a binary star, and even 100% if we also take into account planets. And then, we also, as I showed, have observations that show the indirect presence of companions. And then with the hydro simulations, we confirm that these patterns can be created by companions. So now that we know that these outflows are not spherically symmetric and that often there is one or multiple companions hidden in these outflows, this gives us some challenges and opportunities of things to study. So, first of all, it is very important that we have to be careful with one-dimensional models. So an example is that if we estimate the AGB mass loss rate from observations and we assume that there is a spherical symmetry, we can get quite incorrect estimates of these mass loss rates. And this has been done for years. So we need to study what the impact is of a companion and also the non-spherical density distribution of these outflows on these mass loss rates. As the mass loss rate is, of course, a very important parameter as it determines also the stellar evolution. So then, as said, both AGB stars and planetary nebula harbor also very complex morphologies. So now that we know that AGB stars also have such complex morphologies, we should try to bridge the gap between these AGB stars and both AGB stars and planetary nebula. So the first thing we should study is there are still some problems with the understanding of orbital evolution of both AGB stars and planetary nebula. We, for example, see that there are a lot of quite highly eccentric periods in these both AGB stars, and it is still not understood how we get these eccentricities there. But then also we want to understand how these both AGB stars and planetary nebula get these complex structure morphologies. As for example, here you see what a binary post-AGB star typically looks like. So they have a circumbinary disk, and there's also bipolar outflow from the companion, which also has an accretion disk. And it's not well understood how we get these morphologies. And then when you put the images of planetary nebula next to the images we have now of these AGB outflows, you can see that this already resembles a bit. So by studying these outflows, we also hope to learn something about how these outflows are shaped, because it's probably sort of the same mechanism being binary stars. Okay, so then the third thing we are actually studying mostly in our team is now that we have these high resolution observations of these AGB outflows, we also should try to understand what is happening in these outflows themselves. So here you see an overview of what me and my closest collaborators are working on. So you can see that we both have some rather observational people that are mainly focusing on the observations we have from this Atomium project, so studying the molecular line observations. But then there's also a lot of theoretical, more modeling related people. And by working together, we hope to get like our string together of both modeling and observational expertise to try to understand what is happening in these outflows. So throughout the talk, I will try to go over all the parts of these slides to give you a good understanding of what is happening. And I'm going to start with the AGB wind model. So the model we are using to understand how a companion can shape the winds of these outflows is a model with the code Phantom, which is developed here in Monash by Daniel Price. And this is a three-dimensional smoothed particle hydrodynamics code. Together with Daniel Price, Lionel Sis has developed an AGB wind routine in Phantom that we are now using. So in this wind routine, we have a gravity-only AGB star and a companion that are represented by zinc particles. And then from the AGB star, we have some boundary shells from which an SPH free wind is launched. So just a lot of SPH particles launched from there. Already some models have been published using this method, but now we also have a small improvement, or not small, it's important, but an improvement to these models that we included also H1 cooling. And these are the models that are still in preparation and that I'm also going to show you today. Our AGB model itself is also still under development, mainly by Lionel Sis and Mats Esseldeurs. So, for example, in the models that I am using, we have a wind that is launched as a free wind, and you see the velocity law here. And we know that this is not very accurate yet. So that is why in his most recent paper, Mats has MATS has used some sort of ray tracer to get a better estimate of the radiation force that is actually launching this wind. And he did this by using some different approximations, and you can see here the velocity laws of these different approximations. So that already has a strong impact on the velocity of our wind. So this is important that we keep developing these models to get a better and accurate wind model. Then LeoNLCs also included some form of dust nucleation to get a more accurate wind launching. And in the future, they also hope to include pulsations. And then, as I said, we already have some H1 cooling now, but in the future, we also need more accurate cooling and heating mechanisms in our model. But if you are interested, Lionel gave a nice talk about this at the Phantom conference, and you can also see that one online. So now I'm going to show you some of the results we already obtained with these models. So in our previously published papers, we explored a certain parameter space. So we made different simulations in which we varied the semi-major axis, the AGB wind velocity, the mass of the binary companion, and the orbital eccentricity. So in these models, we did not yet have H1 cooling. In one paper, we focused mainly on the binaries in eccentric orbits, and we studied in detail how various wind structures can form close to the companion and the AGB star, and how these various wind structures then result in different global morphologies in these AGB winds. And then in the other paper, we more focused on the impact of the companion on, for example, the terminal wind velocity. And we also studied how a classification parameter can give you a good estimate. So if you have the input parameters, can give you an estimate of how complex the global morphology will be. So in general, if you have a companion, this will impact your wind in two ways. So at first, a companion will induce an orbital motion of both stars around the center of mass. And as this AGB star is moving while it's launching the wind, there is a Coriolis force that tends to create already a spiral structure in the wind. And then you also have the companion itself that is also orbiting and is attracting wind particles, and this also tends to create a gravitational wake behind the companion. So you see this already here in this image. Then in general, the impact of the companion will be stronger if its mass is larger, because it attracts more wind particles. If the orbital separation is smaller, the wind velocity is lower, or if the eccentricity is higher. And here you see a classification parameter that we studied in Maas et al. That nicely combines all of these parameters. And if this epsilon is very low, then we expect that the impact of the companion will be also not that strong, while if this epsilon is very high, it indicates that the companion will strongly influence the wind and attract a lot of particles around it. So I'm going to show you some examples of our models. And in all of these examples, I'm going to show you a binary system with a 1.5 solar mass AGB star and a solar mass companion at an orbital separation of 6 astronomical units. We vary the eccentricity and we vary the wind velocity of the AGB star. So I'm always going to show you 2D slices of our 3D model, and I'm going to show the density distribution. So in most cases, it's going to be the orbital plane slice, so this one that you see, so you see a view from there. So this is what you see here, so it's a density distribution in this orbital plane slice. And it's two different models, one in which the wind velocity is high, one in which the wind velocity is quite low. And you see in both cases that, a bit as expected, we get this nice approximate Archimedes spiral. But then if we rotate our view, and we look at a 2D slice and an edge-on view, you see that these two models, although they looked about the same in the orbital plane view, they are still quite different if you look at them edge-on. So in the first one, you see some sort of concentric banana-shaped arcs, and in the second one, these structures are bicentric and elongated rings. This elongation is important because something that we want to study is the deviation from a global spherically symmetric density distribution. So if we have an elongation, we should study this. and this elongation is often referred to as flattening. And this flattening occurs because you have these two stars that are orbiting, and as this AGB star is then launching the wind particles, there's also the centrifugal force due to this orbital motion that tends to flatten the wind. So because as the particles are sent out by the AGB star, their velocity vector gets an additional component in the direction of the orbital plane, which is this orbital velocity of the AGB star. So here you see the width and the height of one such ring structure, and you see here that the width is larger than the height, so we have a flattening. So then we can go back to the orbital plane view, and we can zoom in a bit to see if there is a difference between these two models. So in the first one, you have the companion here, and then the structure behind it is a two-edged spiral structure. So as the companion gravitationally attracts material around it, there is a velocity dispersion in this wake that is formed behind it, and that is why you get these two edges of this wake. But then, in this second model, you also get one quite dense spiral structure behind the companion, but there's also a bow shock spiral that originates in front of the companion. And that is because this companion gravitationally attracts more material closely around it. And then this bow shock spiral is actually also a two-edged spiral, as you can see here. And in this way, if we zoom out again, we see that there is an approximate Archimedes spiral in both of these models. But we can also zoom in a bit closer. Then you see here again this two-edged spiral. But here, if you look close around the companion, you see there's a very high density region. And that is because there is an accretion disk forming around the companion. Here you see this accretion disk again, and if you plot the velocity vectors here, then you can see that material is spiraling inwards towards this sink particle of the companion and can also be accreted there. So this confirms that we indeed have an accretion disk. And if we look at this edge on, then you see that this accretion disk has a flared shape. In the models that have been published already, we did not have these accretion disks, and that is because we did not have this H1 cooling included. So here you see a temperature plot of a model that in this case is with H1 cooling. And you cannot see it here, but in the density plot you see that there is also an accretion disk here within this bow shock. Whereas in our previous models, the temperature just became extremely high around this companion sink particle, such that material was just being expelled outwards, and we got some more irregular morphologies. This one, for example, becomes a square-like morphology in the orbital plane. Okay, so then we also studied what happens in eccentric binaries. It's important that we also try to understand this, as we know there are a lot of post-AGB and planetary nebula that are in eccentric binaries. And we also have some AGB morphologies of which we think that they are also created by eccentric binaries. So in eccentric orbits, the orbital separation varies between its maximal value at apastron passage and minimum value at periastron passage. And then this variation in orbital separation also induces a variation in the orbital velocity of the stars. And this makes that the wind-companion interaction intensity is very phase dependent. And this complicates everything, of course. So here you see an example of a morphology in such an eccentric binary. So in the orbital plane view, and actually also in the edge-on view, the first thing that you see is that we don't have these nice, quite symmetric Archimedes-like spiral structures, but we see some strong asymmetries. And then we also have some characteristic patterns of eccentric systems, which are low density gaps, so these darker regions in between the spirals, and so-called bifurcations, which are locations where two spirals seem to split up or come together, and these are just the edges of these low density gaps. So here you see an animation of these models, so you can see a bit how this evolves and how these low density gaps, as they go outwards, they just disappear because spirals start to overlap, while in this other side, the spirals just overlap for the beginning, so you never get these low density gaps. If we then zoom in again, on the stars and see what happens close to the stars. You see that there's this strong phase-dependent wind interaction with the companion, which makes that the structures here vary a lot depending on where the companion is located in the orbit. So the stars are in upastron passage if the companion is here on the left side of the AGB star. So, in periastron passage, so close to each other. And because of this close encounter, the companion starts to accrete a lot of material around it, such that here a bow shock structure is formed and an accretion disk. But then as the companion orbits further towards apastron passage, so where the stars are far away from each other, this bow shock actually gets detached from the companion star because of the interplay between this strong variation in orbital separation and the strong variation in orbital velocity. And then as the stars here were quite far away from each other, after this bow shock gets detached, a two-edged spiral structure forms. But next to these quite characteristic eccentric morphologies, we also have some other type of morphologies, which are just very asymmetric and a bit more irregular, such as this one. So we can also take a look here at what happens close to the stars. And then you see that because the wind velocity here is lower and there's again this high eccentricity, this interaction becomes very strong and very complex. So as the companion orbits around the AGB star, you again get these different structures because the interaction changes. And you get just a lot of complexities here. But you can also note that the companion is still surrounded by an accretion disk throughout the entire orbital period. Okay, then here you see an example of a simulation in which we chose a very high eccentricity together with a very large orbital separation. So you can see the values here. This is also very interesting because in this case, the companion is for a long time just quite far away from the AGB star, and then it has each orbital period one very intense close encounter. And as you see, this type of setup creates some sort of spherical structures in the wind. And we actually made these simulations because Thaisa, who's working here, was studying some atomic observations of the star W Achille. And in these stars, from the observations, we think that there is such a companion in such a wide orbit with a very high eccentricity. And in the channel maps of these observations, we also see some of those similar circular structures arising. So it's very nice that in this case, our simulations can actually help to confirm that there is indeed such an eccentric companion in these observations. But if you want to know more about this, you can ask Thaisa or wait for her paper, which will be submitted soon. What is also interesting is if we zoom out, we get this nice morphology with all these concentric spherical structures. And recently we also, not we, but there was an observation with the James Webb Telescope of this Wolf-Rayet star that is known to be in such a very high eccentric binary orbit. And this means that we see similar structures, so they will probably also be caused by a similar phenomenon being this highly eccentric binary. Okay, as we are now in a good way of our understanding of these binary simulations, we take a step forward and we also want to understand what is happening in hierarchical triple simulations. So hierarchical triples, that means that you have three stars, but you can sort of see them as two binaries. So in our case, we have one close inner binary that consists of the AGB star and a close companion. And then there's a third star, and for the orbital movement of this third star, you can see this inner binary as being like one star that is located in the center of mass of this inner binary. So because of the presence of this third companion, this inner binary also orbits around the common center of mass, and this complicates the orbit of the AGB star that is launching the wind also. So in the simulations we have a 1.6 solar mass AGB star and then a close companion at 5 AU. And then the outer orbit is 35 astronomical units. We vary the eccentricity of the orbital of the outer orbit and the mass of the outer companion. And we also vary the AGB wind velocity. So we have a large set of models. But this is still work in preparation, but I'm going to show you something already that you have an idea of what is happening here. So here you see twice the same simulation, but zoomed in here on the right so that you can see better what is happening closer to the stars. And you see that the inner binary is again creating this nice Archimedes spiral structure, as we saw in our binary simulations. But then you have this additional star on top of that is creating an extra spiral on top of this inner, quite compressed spiral structure. And this outer spiral is also strongly affected by this inner compressed spiral, which you can see from these waves here in the outer edge as it's like interacting with all these wakes from the inner spiral again. So here you see a bit better what is happening than in the global morphology. So if you zoom out a bit more, we get this type of morphology. So up until a radius of about 1000 AU, we still see the signature of this inner dense compressed spiral, and then the outer spiral just takes over. We can also increase the mass of this outer companion. So instead of 0.6, we go to a 1.5 solar mass star. And because this third star has a higher mass, the orbital movement of this inner binary around the common center of mass becomes larger, so becomes stronger. And this strongly affects this compressed inner spiral structure, because this inner spiral is then also sort of moving around the common center of mass, so it's like pushing its spirals a bit in this way, and then you get a snail-like structure instead of this nice Archimedes spiral, which you can see quite well here in this part. So these simulations are not only very interesting in a scientific way, but they are also nice and appealing to look at. So you can note that it's quite relaxing to look at them, so I will let you enjoy a bit here. There was music, but I don't think it's working. If they are eccentric, then it gets a little bit more messy and it's a bit less like to look at them, less nice to look at them. Okay. So that was everything I wanted to say about the results of this hydro simulation. So we can come back to this slide and see what everyone else is also working on. So to reach our final goal and to learn something from the observations from our simulations, we want to improve our AGB wind model to make it more realistic. And to do that, we also want to include chemical calculations to our 3D hydrodynamical simulations. And that is what Silke Maas and her collaborators are working on. So it's very important that we also try to model this chemistry in 3D, because, as I said at the beginning, we want to understand what is happening in these AGB outflows, as they are these rich astrochemical environments, making them very interesting astrochemical laboratories. And we need to understand them if we want to understand their chemical enrichment to the interstellar medium. But then also, since we see that we have these three-dimensional density structures, such as these spirals, for example, these density structures also impact the chemistry. So it is necessary that we also try to model this chemistry in our 3D models to understand the chemistry and the observations in a correct way. But this is very difficult. It has been tried already, but not yet successful. And that is because if we want to solve the differential equations of this chemical kinetics, this becomes very computationally intensive in these 3D complex simulations. So that is why Silke and her collaborators want to accelerate this process with the use of an emulator and a neural network. So by emulating the chemical calculations, we would get the chemical abundances in a fast way without doing these very expensive calculations. So the idea is that in a simulation, you give the physical state and the abundances at the time t, and then at the next time step in the simulation t plus delta t, you just emulate these abundances without doing computationally expensive calculations. So to do this, they will train this neural network with the use of 1D models, and they will include about 500 species and about 6,000 reactions. So what we are also working on is if we want to couple our models to the observations, we also need radiative transfer. And here Frederik de Keuster and Thomas Keulemans are the developers of the radiative transfer code Magritte. And Magritte is an open source software library for this three-dimensional radiative transfer, and it can easily be applied to models such as our phantom models. So what it does is it calculates the line radiative transfer, and it can do non-LTE calculations with the use of an accelerated lambda iteration method. It does not yet include dust, and it is an MPI and OpenMP parallel code. So to use Magritte, you can do that both with SPH models and grid-based models, as it does not require a particular input grid, so the input model does not have to be in a grid. So all it needs is a point cloud, and then it will use a nearest neighbor information. So Magritte optimizes this discretization by remeshing the inputs. So you can see an example here. This was a grid-based model, but then by remeshing it, you get something like this. And it does that in an optimal way to calculate this radiative transfer in these models with quite complex morphologies. Recently, this has also been optimized by Thomas Keulemans, which accelerated this remeshing and the calculation of the line radiative transfer with a factor of 50. So then, to actually calculate the line radiative transfer, it uses a ray tracer, which you can also see schematically here on the image. And this ray tracer is also the one that has been adapted now in our phantom wind model by Mats, as I explained at the beginning. So to give you an idea of what we can do with Magritte, I'll show you an example. So what you see here is an ALMA observation of the star erarchical, which, as you can see, has a very complex morphology with a lot of complex arc and spiral-like structures. So what you see here are the channel maps of the CO221 line. So in each of these 2D images, you see all the material that is coming towards you or going away from you with a certain velocity. And if you put all these images next to each other through an animation, you get a better view of this 3D complex morphology here. So if we try to unravel what is happening in this star and what is creating these structures, we can try to compare this to our simulation and see if we see some similarities. And that is where Magritte can help us. So here you see again the erarchical observation, and then next to it you see a synthetic observation made with Magritte of one of our triple simulation models. However, it is still very difficult to compare these observations with our simulations and synthetic observations. First of all, because we are still developing our phantom wind model, so we do this step by step by including more and more physics. We gradually increase our understanding of what is happening, but we are not yet there that we get the same complexities as in these observations, where there are pulsations, for example, or clumps in the wind. And we also want to model the chemistry, of course. But even then, if we have the full model, it will always be difficult because of these complexities in these AGB outflows that make it very hard to know which model you want to run that will actually be comparable to these observations. So the approach that I showed here is the forward modeling, so trying to make synthetic observations of these models that might then resemble the observations. But yeah, I just explained the difficulties of this approach. So that is why Frederik de Keuster and his collaborators will also try to do another way, being the inverse modeling. So in this inverse modeling, we want to go from our observations to two models instead of the other way around. So this would mean that we have to make a deep projection of our observations. Because as I showed you, what we have from our observations are 2D images, like the ones I showed from erarchical. These are these 2D channel maps. So for each point in such a channel map, we have a two-dimensional coordinates, and then the third dimension is a velocity, a projected velocity. So if we want to make a 3D model, we have to go from these coordinates to fully three-dimensional coordinates. But as we are limited with the amount of channel maps we have here, we will also always have to interpolate to some regions. So we can never be exactly sure of the model we get, which means that we also need an uncertainty quantification. But by the use of this approach, we hope to get a better view of the morphologies of the observations we have in these 3 dimensions. And we hope to, in that way, also learn a bit what is happening there and how we can model these structures. So I hope that this gave you a bit of a good overview of what all of us are working on and how we want to reach our goal together to understand these complex ALMA observations. So what I want you to remember from this is that these AGB outflows are very complex, and that these complexities are mainly shaped by the impact of the wind with one or multiple companions that are hidden in the wind. Thanks to Phantom, we are already good on our way to understand how a companion can structure this wind in both binary and triple systems. But to reach our goal, we still want to develop our AGB wind model, and we want to do this by step improving it and adding more complexities to also improve our understanding, and then also couple it to chemistry. And then with the radiative transfer solver Magritte, and we also want to post-process this with an ALMA simulator. And then we also want to use a deep projection to reach our final goal and get an understanding of these observations with the use of our simulations. And then finally, if someone is looking for a job and is interested in hydrodynamic modeling or just computational things, then you can always email Leen de Sien or talk to me, because we have a postdoc vacancy in our nice team. So thank you for listening. Mostly the general pulsations of the AGB stars, because I think the other type that creates like these nice shells, we already understand a bit what is happening there. I mean, we know that this will create these shells, but I think in the future they will probably also see if we can implement that. But it was mostly like the general pulsations. Yeah, but yeah, there's many things. Okay, yeah, go ahead.
So hi, the talk was great. So with the accretions onto the companions, do you also see any reaccretion onto the AGB star itself?
No, but that is maybe also, okay, like in the real world, you have also like sometimes Roslope overflow and these kind of things. But in my models, we have a free wind, which means that we actually put off the gravity of the AGB star, because that's the only way the wind can get launched that easily. But maybe in our future models, if we include these better ways of launching the wind, we might get things like that, but not yet. You also had it?
Yeah, I was just wondering, so when you're talking about the chemical implications, are you expecting that the shape of the outflow is impacting like, the actual rate of mass loss and so the surface properties, or is this more like once the material has left, it's the molecular stuff that's going to be impacted?
Wait, so you mean the impact on the chemistry or on the mass loss rate, or both?
As in like in 1D models, say we calculate the yield, so the amount of mass that's lost from the surface. Yeah. Is the impact on the chemistry, like, sorry, I'm not explaining this very well. like in terms of like the cooler, so like the cooler chemistry going on above the surface, or at, like, is it changing the mass loss rate, which is going to change the amount of mass that's lost, and that's going to impact that?
Okay, wait, so I'm not sure if that's gonna answer your question, but like mainly the impact of the mass loss rate, what I understood is that the companion itself can just enhance its mass loss rates by angular momentum things, and the estimates that may be incorrect from these 1D approaches can also be because if you assume that in all directions you have the same density, but this is maybe incorrect because you can get, like if you have this flattening, you can also have an equatorial density enhancement, which means the density is higher around the orbital plane. So then it strongly depends if you are looking like through the orbital plane or looking through the poles, that you get a different density and then also different mass loss rate estimates. So that is also important. Is that a bit answering your question?
Yeah.
Okay, good.
So one thing I've learned from the Phantom workshop is that with the ALMA observations, for a protoplanetary disk, for example, they're looking at the dust emission from the structure. Is that also the case for these outflows? And if that's the case, do you need to incorporate account for dust in your radiative transfer?
Wait, so the ALMA observations we have are the molecular lines. So it's like the CO line especially represents like the density structure. We're also looking at SIO and these type of molecules, so I think it's different. But maybe Taisak can help you with that.
We only see dust very close to the star with ALMA, not like you do with the protoplanetary disks, whereas with the observations molecular.
Okay, and so in your radiative transfer, are you looking at those emission lines in the
Yeah.
images you've shown?
Yes, so the one I showed was the CO emission line, for example. But yeah, we can also model others. Yeah, so this is the same line then as an observation.
Yeah.
So in this thing, so you said lots of the left one was very complex, but do you have any ideas on how to, what may be the extra ingredients you need to?
Well, yeah, not really. Like we have no idea what is happening here. For the moment, we thought because it's so complex that maybe it's a triple star. So that's also a bit why we started these triple simulations. And yeah, I mean it adds extra complexity, but it's not that it's really similar. So yeah.
Like, it could be like a tilted. I think your triple simulation was a coplanar.
Yes. Maybe it's.
To me, it looks like a tilted.
Maybe. Why do you think that?
You have these all sorts of shells going different ways.
And that is maybe, yeah. I tried to model like one or two of these triples where you had, I think I had the AGB as a single and then there was this one. But it's just that if we want to analyze what is happening here, these models became a bit too complex to understand it. And also, if you get coplanar things, then you can nicely see the slices, but if it's non-coplanar, it was difficult. So we're starting with this, but yeah, it's interesting to hear it. Maybe can be that. Yeah. Yeah.
So when you're adding in pulsations, are you going to add dust at the same time?
So now there's already some dust nucleation implemented, so then the pulsations will be in that model where there is this dust nucleation. Yeah.
They are observed coupled in AGB stars, so I imagine that one without the other would be, be less realistic.
I think there's like different approaches to include this pulsation. Like the simplest way would be just, it's not simple, but that like do something with the input velocity to make it pulsate a bit, but that's not the way Lionel wants to do it, so I think it's indeed more complex with this coupling. But, yeah.
So at the end you showed us about this projection where you only have the velocity as the carrier.
Yeah.
How can you deal with things where if there's a big ambiguity and say two parcels along a line of sight moving at the same velocity? So usually when you do this deep projection, you have to assume some kind of velocity law, but of course for observations you don't know what it really is.
Yeah, that is also within these uncertainties.
Right, so it's not just where it is located velocity, but it could even be ambiguities that you can't pinpoint.
Yes, indeed. Yeah, I think the idea would be to get as much info as we can get from the observations about the velocity. But yeah, the deprojection is different if you assume constant velocity linear or like, so yeah, indeed, that is within these ambiguities and uncertainty. Yeah, but that is also a bit the same problem if we want to go from model to observation to compare it. Well,
it's easier because you can
yeah,
go this way.
yeah, it's easier, but yeah, it's just,
Forward.
that is one of the,
Say that's
yeah, it's one of the,
straightforward to do
yeah.
this way.
it's one of the things that make it so difficult to understand what is like the 3D morphology of the observations, and like to know which structures that you can see in the following channel maps that are actually like the same structure or not. That depends on that, so that makes it difficult. Yeah.
Any further questions?
Just I'm curious about this little accretion disk around the companion. Is there any like observational evidence for like maybe a jet or something processing in an AGB style?
Wait, I think there is, yes. Wait, okay, I have to remember a bit. I remember that from last time we had an atomium meeting with all of us. There was one, Sarah, do you remember which one it was? From Miguel? Which one? Bio and Gru, yeah, I think. Yeah, so that we see indeed like that there are probably disks. I'm not sure about jets.
It's got bipolar jets in the forest.
The big wide ones are like narrowing fingers.
Fairly wide. But also aimed at us.
Like,
They were happy I had an accretion disk.
So maybe I can ask a question about triples because it's fun. So yeah, I think you already mentioned that here you're choosing a coplanar triple, right?
Yeah.
I guess it's probably easier and probably it's fine because I think if you contest, I think it finds really coplanar triples like which are compact. But they also like choose like circular orbits for both of them.
So the ones I showed were all circular orbits, but we also have some models in which the outer orbit has an eccentricity.
Yeah, so I think that's my point. Yeah, I think also in some of the test triples, I think some of the outer is the big centric.
Yeah.
Also, I think if the period ratio is not that large, it's like 5 over 35. So I think you may induce some eccentricity onto the inner orbit from the tertiary.
Yeah.
So do you look some body integrator for these bodies, or is just like a fixed?
No, this is so in Phantom they are implemented as this hierarchical setup. So just the binary, and then this one is like this one with the center of mass is again a binary. But the orbits can evolve a bit, but it's just implemented in this hierarchical way. So not an n-body code.
Yeah, okay. Maybe like a last follow-up before we leave. Am I allowed? I'm going to check something. Yes, I think you mentioned that you tried like, at least in binaries, you tried both like circular and eccentric orbits, right? So to which degree you can kind of, I mean, what interesting you need to have so that you say, oh, this is not circular. So what's like the threshold, like 0.1 or something like that?
It depends a lot, I think, because if it's like, okay, for example, in some of the triple systems where I had an eccentric outer orbit, you can barely see that it's eccentric even if you have the 0.3 eccentricity. I mean, this is a circular, but just to give you an idea, whereas in these binaries, it's much more clear. So it depends also how close they are and how strong this interaction is, if it becomes asymmetric or not, and if you can even see that it's asymmetric or not from models or observations.
Okay, so it's like a function of the separation of the binary.
Yeah, like more of like how strong the impact is of the companion, like this interaction. Yeah.
All right, I think I've approached you enough, so let's thank Jolien again.
Thank you.